good morning, everyone. It gives me. Is it ready yet? Yep. Okay. Good morning, everyone. It gives me great pleasure to introduce Professor Deb Roy from Multimedia Lab. Happens to be a fellow media fellow, and we discovered that we graduated the same month from Media Lab. And he builds robots that talk for a living. And he's here to talk about it all today. Without much further ado, Deb Roy.
Thank you. Well, thank you for inviting me to speak today. I've given my talk a title that is designed to get me into trouble and hopefully start some conversation. And I understand that's part of the idea of these talks. And I am going to be talking about work that's joint with several of my students at the lab: Peter Gorniak, Caillou Xiao, Nick Mavridis, Andre Ribeiro, Mike Fleischman, Niloy Mukherjee, Josh Juster, and Stephanie Telix. I thought I would start with a little personal note of my first experience with NLP. This goes back to early 1980s day in Winnipeg, where I wandered into a Radio Shack and discovered this strange new machine called a TRS-80. And I was excited. I was going to make communication with a new species and tried to introduce myself and got back this strange response. And I didn't know what this strange word syntax meant, so I tried to reformulate, wasn't getting anywhere. And it became embarrassingly obvious pretty quickly that we were not speaking the same language. And it's sort of an early disappointment with these machines I thought I could talk to, and something not quite right about my model of what was in that machine. So it turned out that I needed to speak its language because it didn't speak mine, and it had these sort of surface level labels that looked like words, but in fact they were very different from the machine's point of view than mine. So that kind of led to a question, which I've been bothered by for a long time now. How can machines understand the meaning of words and speech acts? Somewhat like the way we understand meaning. And to explain the title, How Do We Build Meaning Machines? Something that gets at that underlying intuition or sort of problem. And hopefully by the end of this hour, you'll have a better idea of what I have in mind. So one possibility for getting a machine to understand meaning is to somehow encode whatever's in a dictionary into the machine. So it seems reasonable. When we don't know the meaning of a word, or depending on the book, the phrase, we can go look things up. And there is an obvious problem from a machine's perspective, which is one of circularity. Of course, in a dictionary, all you have are words pointing to words. So here's Webster's definition of push, which is to press forcefully against in order to move. If you look up force, you'll find energy or strength is a definition. Strength is the power to resist force. Energy is defined as strength or force. Okay, so you've got a tight set of circularities. Of course, people find dictionaries useful, but they do so because they have some experience about how the world works and how certain words map into that non-linguistic experience that gets loops like this off the ground. Okay, and so that's kind of the intuition. As Gary said, I build robots that talk, or I try to build robots that talk, or I build robots that try to talk, depending on how you look at it. And so imagine this little tin can robot, and I say to it, push the can to me, and our speech recognizer does its job and conjures up this little piece of symbolic network, a semantic network, whatever you want to call it, maybe a collection of meaning postulates that are sort of now floating in the robot's head, and the question is, what is the robot to do? We can hack it. We can have some surface level connection from that particular structure to what it should do in this particular scene, given some vision system and so forth. But what's a more principled way to figure out what to do in some physical situation? A very simple one is one of the questions I care about. So words are about the world, an obvious observation, not so obvious how to capture that in some sort of a coherent framework. Second example, just to motivate how some very simple problems, at least I don't know how to think about. Here in Google, I've typed in a query that you can imagine a child asking their parent, what's that place I visited yesterday? And who thinks Google will be able to help us. Well, obviously not. We come up with Tennessee's most beautiful berry pick and farm yesterday, which is not where I was. And we have a hint here. There's some words that are just too common to include in the query, the and I. Well, indexicals and articles, these are common for a reason. They're packed with meaning. They bind speech acts to space and time. Without a framework for understanding that binding, we've got basic problems in dealing with this sort of thing. Now, Google actually cares about this problem, of course, and so having better ways to deal with the situated nature of language is clearly something desirable. And the third and last aspect of meaning that I'd like to bring up is the following. Here's an everyday situation. Speaker says to listener, "This coffee is cold," and we could bring in the thought bubble and say, well, if Grice were to analyze a speech act, Grice would say that this is a purposeful agent that has some goal or perhaps some set of goals that are in some sort of arrangement that this set of words is trying to pursue. Okay, so in some theory of action, which doesn't just include words, it also includes moving your arm and moving around and picking up things and pushing things around, lives these things called words that are being used as part of the purposeful nature of language. So putting those three things together into one picture, this is my problem statement, which is these words have meaning in this context because of two very different apparent types of connections. On one hand, they are purposeful, so there are links to some sort of planning structure, and yet they are situated they're bound to some region of space-time, and they make reference to these objects. And to bridge these two types of links, I take as really a grand challenge for AI, for cognitive science. I'm not going to solve it for you in the next 45 minutes. I wish I could. But I do see this as a way to frame things that captures quite a bit of the everyday intuition of what meaning of words are. There's something I'm leaving out here which has to do with connotations, how I feel about coffee, and something I will leave for this talk, but I think builds on top of this. It's not parallel to. Yeah.
That's along the lines of the question I wanted to ask. When you say the agent has purposes, how broadly are you going to define it? Is communicating an idea one of the purposes that you will look at? Or no?
I would prefer to think about, and I'll get to this later in the talk, sort of more a call for than specific proposals for finer-grained game theoretic framings. I don't think we can analyze language without it. So I don't just mean communicate for the sake of getting across a description. I want to give you a description of the world, for example, that this coffee is cold because I have some goal in mind, such as getting hot coffee, or perhaps answering a question, like is the coffee...
There is also an estimate of the listener's empathy.
Yes. Yep. So
it's not just what purpose I have, but whether you understand.
That's right. Yeah. So there's absolutely some, I think, very rich, the best framework I can think of, game theoretic notions of what's this person's payoff. If I convince them of it, are they likely to act upon it or not? What you'll see in the primitive systems we're building is some assumed social roles. So one very dominant sort of model is caretaker-infant, if we're thinking about learning, or something like master-slave, where you tell the machine it is its social role to do what you want, right? But that leaves open issues of inference. What is it you want? And again, binding that to, on the other hand, having some model of context. So this is just a way of what I might call meaning holism. Okay, what's sort of a holistic picture. So what I'd like to do now is spend a few minutes defining a term that gets thrown around a lot, including by me, called grounding, which is a way of describing sort of again, at a very high level, a way I believe we can think about connecting meaning to words in machines. And then I'm going to give you an overview of a whole set of systems we've been building over the years. Rather than picking one and going too deep, I'm going to give you sort of more the flavor of the kind of algorithms and representations we've been developing. And then really for the first time that I've talked about this, kind of give you a sense of a theoretical framework that's emerging from implementation. And that'll be a little risky because I haven't tried to talk about it before. And then end with some of these questions about structure of purposes and kind of where do you stop, because you have to pin them down somewhere. So here is my definition of what it means to ground not a word, but a belief. Is a sort of an atom of knowledge on top of which language is going to sit. And without saying too much, because I'll unpack it with examples in a minute, to hold a belief about the world is to both be able to make predictions about that world and also to have causal explanations of where that belief came from. Okay, so there's a cycle. So to make it concrete, you have some thing in the world, like a cup or a fly. There's some causal, physical explanation governed by physical laws, photons, electrons flowing, that impinges on an agent that's holding some information structures that allow it to now make new predictions about the world, which are only available to it through the same channels by which it formed the beliefs in the first place. Okay, so there's a loop. For those of you who've been, a couple of people mentioned that been thinking about similar sorts of problems, there is a use of grounding. I don't think I have. Oh, I do. Which kind of looks like this. To ground the meaning of cup, you have a camera, you put a cup in front of it. In the agent's mind is some sort of a model of that cup because you have a vision system that recovers some sort of a CAD model or perhaps a 2D model, and then you attach a label to that model in the head, and that's one possibility for what it means to ground the meaning of the word cup. There's a problem with that, which is well known in sort of theory of representations, which is this. I try to capture in this picture. Here's an agent, it's a little robot with cameras examining this little block. If what this agent does is construct some model in its head of that block, it just pushes back the question of what's interpreting that model. No different than how does this guy interpret the block is, well, now it's got a picture in its head of that block. What's looking at the picture? Okay, and if you have a model of representation that's just model building, or essentially building descriptions, you can not get out of this regression. Okay, so the picture I give of that cycle is going to address that. So just to finish building the intuition of what I mean by grounding, let me give you an example of the kind of models we're building, first at a very, again, cartoon level, and then show you some of the implementation. So I'm going to unpack again the meaning of some of these terms as we go. But here's a can, or maybe a cup, viewed from some angle. And I like to think of that as a sign of the cup. Okay, this is, we're going to...
The what of the cup?
A sign. Mm-hmm. So that's a visual sign. It's a set of photons that are caused by the presence of that cup that are projecting onto my sensory apparatus leads to this sign. I can have a set of expectations of where I should see parts of that sign given other parts if I believe that this sign is actually out there. Let me just see what I've got here. Let me just move forward. So these arrows are showing expectations of, given some particular view of a cup, what other views I expect, if in fact there is a cup out there in the world. Okay, so here's an object. I see it from one view. I expect if I move, I'm going to get a different perspective as I shift around my perspective. So this is bringing in a kind of action. This is obviously straight out of active perception. And we've implemented, some of you, I think, work on computer vision. And again, I'll tell you a lot more offline if you're interested. We've been doing tests with the Columbia coil database. So this is an actual output from our system tracking cups with occlusion and with shift in perspective, where we essentially have a set of graphical models that are making predictions of edges given the presence of other edges and doing handoffs between these different graphs. And we are getting very decent tracking results on cups. So we have specialized trackers for different objects. So let's bring back our our creature, which is now examining this object and has this little network that's instantiated that is trying to explain away and make predictions of what it's going to see, and introduce a second modality, a modality that seems to come naturally prior to vision is touch. So it's got 3 fingers. So each finger is going to press with some amount of force on the object. Here we've got lots of force compared to this. So we've got light gray versus dark gray. Depending on how the object looks, okay, if it looks like this versus this, if I do the same reach gesture, I'm going to get different touch impact. So that's a touch sign, okay, exact parallel to the visual sign. And there's, again, predictive links between them. And this is a little video to show you our current, one of our hands that's building up these little touch signs and building up correlations with the vision. And now we get to a point where what I'll claim is when you put these 2 modalities and whatever other modalities are available to this particular agent together, you have an interesting structure to which you can bind a name. Okay? And I'm going to have to say more about what are in these arrows, but essentially, if I say to you, there is a cup in front of you on the table, so just an assertion about the existence of some entity in the world, roughly something like this structure I'm positing is instantiated. Okay, a set of expectations that if I do X, I will get such and such sensory data, signs, back from the world. And that's all I've got. So this is a theory. It's a little structure that's instantiated in the head to explain what's happening in some context. And down here are a couple of sample actions that a robot might want to take, like pushing around cups, carrying cups, giving cups to other people, which is sort of a collapsed view of a goal structure. The important thing here is, as is well known from robotic control theory, if you want a firm grasp of an object so you can manipulate it, you want 0 torque, 0 force grip points. So if you have, for example, this grip where one of the fingers is not pressed as firmly as the others, if you try to lift, the object's likely to slip. Okay? That means that from a functional perspective, what you can do with a cup, these touch signs are highly significant. Some will facilitate a particular action, others will not. So if you want to think of what an object is with this view in mind, it's essentially what you can do with the situation given the set of beliefs you hold. Right now, I see it in some perspective, therefore it's more likely to lead to this touch sign, even though I haven't touched it, which means there's no link to carrying. So I'm going to have a hard time carrying it.
Should we understand that everything up, all of the nodes up here, including the word cup, are observables in a graphical model?
No, no. And I'm going to unpack that. In fact, I'm probably going too slow here. But briefly, in case I really rush in the end, which I sometimes do, let me answer it while I'm still calm. There's a notion of there's 2 types of beliefs in this particular framing. One is a discrete belief, which is the result of a categorization process, which is purely a theoretical construct. It's a theory in the head. For me to interpret there's a chair there, I have to make a decision and create a particular interpretation of that visual sign, or if I go over and touch it, the haptic sign. And that construction process is purely in the head. There's no observable. So that's the latent variable that then licenses a set of beliefs that are structured around it. Okay, so on to some experiments, and I seem to recall I put too many of them into these slides, so I might go quickly through some of them. Here's the thing that holds together all of these systems I'm going to briefly fly by in a minute. On one hand, we've got the symbol processing view of computation and computational intelligence, where sort of one key piece of it is knowledge equals symbolic description. And there are people who've done a lot of work in robotics and reactive planning and so forth who will rail against that view and say it's just all wrong. There are no representation. Intelligence without representation was a paper a colleague of mine wrote a few years back. But if you're trying to build robots that talk, you can't get away from that because words are symbols. If anything is a symbol, it's a word. And if I want to tell you what I'm seeing right now, of course I'm describing the world through symbols. I see no way to get away from that. On the other hand, you and I are embedded in a physical world that's noisy from our internal perspective, and we deal with it. And there's all sorts of unexpected things that happen, and we deal with those. So you can't get away from sort of a control theoretic view. So let's pick some problems that uneasily sit between these two and see what kind of progress we can make in connecting them. So that's sort of the thing that's the unifying framework. So this is work that I did several years back as part of my thesis work at MIT, where I started off looking at how infants learn language from their caregivers. I had a group of parents, mothers come in with their pre-verbal infants, saying making recordings like this. So we have spontaneous, natural speech. And what I did in brief was took those raw audio recordings, built a little robot, which you'll see in a minute, that could examine these objects. So we had streams of video of 3D objects, much cleaner video than it was audio, no transcriptions, etc. And I played around with some algorithms that, in a nutshell, use mutual information across the acoustic and the visual stream in order to segment the speech and create a lexicon where each unit in the lexicon had a hidden Markov model of a word, or in general an acoustic sequence, and some sort of I developed these shape histograms and color histograms, little models of shape and color that were paired. So hopefully we'd send something like doggy, and this would be a set of histograms corresponding to a dog-like shape. Okay, and we got some nice results, ran through real data. I then had some fun and built this little robot. It's actually an Activision platform that was used to gather the video of the objects. This is Toko. He's got a little camera in his eye, and he could move around. You could teach him by showing him objects and talking to him, and then you could ask him to point out where's the red apple. He just knew about single objects, shapes, and colors. So it was sort of the start in terms of where these ideas came from. So, and of course the intuition there is something about the meaning of apple must be what happens when you look at one. That was about as articulate as I could be at the time about why I was doing it. That led to me moving to a synthetic world for a while and thinking a little bit about describing images. Again, in particular, I was interested in spatial relations, shapes of very simple objects, and ambiguity that occurs when you have similar things in a scene where you can't just come up with simple descriptions. So what I did was generated these random images of randomly colored and shaped blocks, and had some poor undergraduates sit down, given one target object, generate descriptions so that someone else would click on the same object. And then we did a verification where people would listen to these descriptions and click. Okay, so we had hundreds of these.
The vertical light blue rectangle.
So there's an example where there was little ambiguity with competing objects. Here there's a couple of green rectangles, so
The dark green rectangle directly below the blue rectangle.
you would often get these landmark target sort of constructions. And over 90% of the data were one of these two basic categories of description. And so the problem was, given a transcription of the speech, so we're not doing acoustic learning here, and given some visual representation, which is easy, of these scenes, because we generated them, but nothing else, can we acquire word models and a grammar to replace the human and generate descriptions of novel scenes? Again, I don't have time to go into details. This is published work, if anyone's interested. This is a picture, though, of the structure that's acquired from that input set, a set of scenes and a set of transcriptions, and the ID of the target object within the scene, which essentially is a set of full covariance Gaussians distributed over subsets of the visual feature space. So this says green and blue. So there's a feature selection problem. putting the Gaussians in the right place to model meaning of words like light, white, and dark. Each of these little clusters of words were then put into a little sequencing grammar. So this is a phrase model that's also acquired. So you can read through this, things like the highest green, I can't even read this from here, square. So the highest green square would be one path. Each path through this being a grammatically correct phrase, each word of which is, of course, grounded out in these little visual models. And then this whole structure is embedded in a layered higher order tiny grammar, which knows how to relate two of these with a spatial relation. Okay.
Excuse me,
Yeah.
could you put on the previous slide? Do I understand that by describing the top square,
Mhm.
things that are in the top square, this has learned some kind of a description methodology,
Yeah.
so that when you test it on the lower one
Mhm.
and you talk about green and stuff, it learns it. I mean, it responds.
Not yet. Here, let me show you in the next slide what the
And
output.
I want to know
Yeah.
also on the next slide, which you just showed,
Yeah.
to which degree is the structure of those machines learned or is pre-compiled in it?
Okay. So let me answer your first question with this slide.
Right.
The purpose of this particular system was, given a new scene and given a target,
Yes.
generate a description.
Okay.
Okay, and so here's an example. We're using concatenative synthesis, which means chop up the input speech. What you're going to hear is a sentence that was not in the training corpus, and this is, of course, not a scene from the training corpus. So this is a little example of what it generates. I'll explain that there is a competing object which it wanted to differentiate from.
Competing, did you say?
Yes, another vertical bluish rectangle. So the blue rectangle or the vertical rectangle or the vertical blue wouldn't do it. And we hear nothing. Okay. Well, what you would have heard, I don't know what just happened to the audio, is the blue, vertical blue rectangle above the lower brown one. Okay,
Above
so
the lower.
brown rectangle. And so it would choose to pick a landmark and give the relative. The reason it did that is when it generated one possible description being the blue rectangle, it then computes how well that describes all the competing objects, computes the ratio, and that's a way to quantify ambiguity, and based on that decides that's a bad description. To answer your question of what's learned versus what's built in, the main learning problems were doing feature selection. There was about a dozen features describing a scene. If you tried to learn a Gaussian over all 12 dimensions, there wasn't enough data. There's only 600 training examples. So picking the subset of features, estimating distributions over those features, then clustering words into sort of both semantic and syntactically compact sets, learning transition probabilities between those, and learning then the transition probabilities between this entire set and the spatial terms. Those were the
So
things.
the structure of the thing was built in.
I mean,
The fact that
the
there's a
layering.
connection from here to there.
No, that was learned.
I thought features.
No, features also. What was learned? Features,
Yeah.
word clusters, transitions between clusters, that was learned. What was built in? The actual features, and the fact that you should treat spatial relations separate from phrase description. The entire fact that there's 3 layers, that was given. Each transition, where to put the transitions and what weights to give them was learned. Which words to cluster was learned, which features to select were
All
learned.
right. So we had originally the possibility of full connection. And
Yes.
the reason that I don't see a full connection is because certain transitions were estimated to have close to 0.
That is correct. And this is a pruned for display. I just set a threshold, so there are more residual probability paths that are, yep. And there's essentially, Let me ask a question. We have the room until 11:30. Should I still try to finish talking by 11, in which case I'm going to be more aggressive on?
You can go.
Okay. All right. Then I'll.
Past the 11:30.
Right. All right.
No.
Okay.
Okay, actually, hold on. Stay on that
Yep.
for 1
Yep.
minute.
By the way, just to give you the content gauge, we're at about 15 to 20% of what my talk has. And then please go ahead.
We'll speed up a little bit.
Yep.
And the phrase model on the right, the spatial description model.
Yep.
I could imagine building this if I could tag all the objects
Hmm.
in the transcription ahead of time.
Yep.
Was that done, or was that also left open?
That was left open. What I mean by I built in the fact that there should be 2 layers
Okay.
was that the learning algorithm was a 2-pass strategy.
Okay.
Pass 1, learn these.
Okay.
Pass 2, assume you've learned them right, learn these.
Okay.
Okay?
And in learning these, you had the
Actual scenes.
the scene with the correct object description.
That's right.
Okay.
You knew which one was the target.
In other words, if the reference description was the vertical blue rectangle above the brown rectangle,
Yep.
then the vertical blue rectangle and brown rectangle
No.
were parsed out and
No.
no.
It only knew the target. It did not know. So there's a target object you're describing.
Right.
If you said the target above the landmark,
Right.
the learning algorithm did not know the identity of the landmark.
Okay.
So in the first pass, because of the statistics of the corpus, there was a lot of bag of words, associative model would pick out sort of descriptive terms. Once it acquired that structure in the second pass, it used it and it identified 2 objects. And then it went back to the scene and said, oh, this is the landmark, and now let me compute spatial features between and use the exact same associative learning algorithm and learn the meaning of to the left of. One more little detail in case you care, words like to the left of, there was a little, there was a agglomerative sort of, islands of words that happen to occur together often were tokenized before the, yeah.
The model is shared between the target and the landmark object.
For the sake of time, I'm going to go forward, and then I'm happy to come back and pop this up. And I almost didn't include describer in the talk. I'm glad I did. I didn't realize there'd be so many questions. So then we did what you suggested. We took that description system and we said, let's invert it. And let's build a system where you can speak to it a description and it will find the object that best matches. So you say the apple on the left, and this was Newt. Newt had a little laser. I've enhanced the path of the laser so you can see. You would talk to Newt and say the apple on the left, and Newt would shoop, laser over and shine his little light on the object you had in mind. And this thing, it's tiny vocabulary, so it would run in real time. You talk to it, and again, I cut the video for sake of time. One detail, which I thought might be appreciated by some of you, so I'll drill in a little bit more. This is some work that's in press right now, and again, I'll just give you the outline story, is in that context of understanding referring expressions, wouldn't it be nice to take the input from the vision system and bias the language model, since we know that the speech is going to be about what's in the scene? Okay, so this is starting to get at some of the interesting algorithmic kind of low-hanging fruit, if you will, when you know you're dealing with a description of a scene. So what we did was to take our little visual analysis engine, which is, again, the vision problem here, much easier than the cup system I just showed you earlier. So you have a set of objects, Lego blocks are what we used in this experiment. The vision system returns a probabilistic description of where it thinks objects are, how many there are, what their colors, what their shapes are. Okay? And since we have this description grammar that you just saw a picture of, we can, of course, generate descriptions of any target in the scene. We can generate multiple descriptions. Each path through those little finite state machines are a different possible description. In fact, we can enumerate, in theory, all possible descriptions and give each of them a weight, because we have weighted transitions, and we can compile them into a language model. So given this scene, here is a likelihood of any possible description given the language model I have of how people talk about this scene. So that's basically what we did. Okay, so visual scene goes to a language model, which is compiled by the process I just described, standard speech decoder, where in the forward pass we are using the language model based on what vision is giving us. And then here's one more little interesting trick, because I like cycles. We can take the partial hypothesis from the forward pass of our decoder, okay, which is obviously multiple possible words that have different confidence attached to them. And we can have a simple model of visual attention, which is, given this partial description, what are the likelihoods I want to assign to each object? So if I say the, well, all bets are off. Maybe any object's possible. I say the red, and that knocks out most things that aren't red. The red square. And so incrementally you can refine your hypothesis of what in the scene is being described. And then we can just reweight all those descriptions and compile a new language model. So that was, there's many variants on this theme. We just picked one path and cut through it. And got some neat results. This is, again, you can download this if you care to. It's a computer speech and language paper in press now. Where here's one typical scene where I've just redrawn them with numbers for the objects. Here's the actual output of one of our decodes. So the large green block in the far right beneath the yellow block and red block, it decoded as in. The summary is that we get a significant reduction in word error rate when you turn the vision system on.
What does the parentheses mean?
The parentheses, okay, so let me now explain what this graph is. For every word that is not in parentheses,
Yes.
okay, there is an update that's happening on the visual attention model. So the system's hypothesis of which object is the target of your description is evolving as the words are being decoded. Okay, these words, block in the far, if you look at the underlying description language model, they were pruned out. They have no visual models associated. So they have no impact on the visual attention. So the way to read this is, when you start off equal priors, the has no effect. So all 10 objects are equally probable. I hear large and then green, and by the time I hear large and green, only 7 and 8, that's 7 and 8. So these two large green rectangles are contenders. There's some residual mass, probability mass, but most of it. So the system really thinks we're talking about one of these two. And then it hears this very different kind of word, beneath, which is handled by that higher level spatial grammar. And beneath triggers a complete shift in the probability mass to 9 and 10, which are these two objects. Because if this large green thing is beneath, then the things above must be the objects we're talking about. Okay, and then we have the yellow block and the red block go off, where it really makes no further tuning of its hypothesis. So as the speech runs through, the system is...
I don't understand. In the green, in the third word,
Yeah.
green is obviously object number, well, I don't know, whatever, 8 or 7, right?
Or-
1, 7, or 8.
But it shifts attention
one-
to the
one
object
is-
in
Well,
preposition.
okay, 1, 7, or 8.
Yeah.
So how come, so...
When I come down...
Still green.
Yeah.
So how come 9 and 10 are most probable?
Because this spatial term...
Yeah. Should target to that. Should target to one of the greens still. Say we want this green.
No, this will tell it to look for things that those green things hold a beneath relation. So...
Maybe I'm wrong. Aren't we referring to the green thing which is beneath the yellow and red block?
Mm-hmm. But this is trying to decode the landmarks, the yellow and the... So you also...
I thought we're trying to specify that it's that green one.
The final output of this entire system will be the green one. But this is just a view of what's happening as it decodes the speech about the landmark, which is the probability mass then shifts to the landmarks that are being described. Yeah.
Okay, so now I understand. So when you say beneath, now the attention is going to go on the next word to one of these.
Yeah.
Now, this doesn't quite accord with the way that people's eye movements work.
With people's what?
It doesn't quite accord with the way that people's eye movements track. So if you give this sentence to a human, if I'm not mistaken, they'll look at the yellow and red block immediately when they hear beneath, and then they'll look back at the green block, identifying the referent, because it's the only green thing which is beneath something.
Yeah. Actually,
Which is not a criticism.
funny you ask, because we've done eye tracking studies and compared the results, and you put your finger on it, which is very different. They're divergent strategies. So there seems to be in humans, first of all, incredible processes. If I put candy and a candle next to each other, by the time you've heard the duh in either candy or candle, right, your eyes are on one of those two with high probability and not all the other distractors. So people like Tannenhaus and Spivey. So Spivey and I've sort of compared notes on this as a model of eye tracking. And clearly one point of divergence is there's a meta-level process which is saying, I'm pretty damn sure what we're talking about here, and cut the rest here, right? Because there's just no ambiguity left. Grice would say, bad speaker, right? You're adding all this additional verbiage, but there was no ambiguity that called for it, right? So these notions of ambiguity, when should I expend more words to encode descriptive information versus not, they're sort of all coming out of, I'm reading a lot into and interpreting the algorithms here, but, and one way to get at that is, the reason we've gone to so much trouble to set up eye tracking facilities we're curious. When humans do generate descriptions, and others follow along the descriptions, what can you tell from where they look? So yeah, that's definitely a link we care about. Okay, remember what we're doing here. I'm giving you language grounding experiments, systems we built. Here's the last one, and then we'll get on to some distilling some underlying principles, I hope. This is Ripley. Ripley is our latest language learning system. Which in terms of the hardware takes a big step forward. So Ripley has a pair of cameras, Ripley can touch, Ripley can feel proprioceptively. Every joint has both position sensors and force. So if I'm holding this object versus I'm not, in these sensors are the ability to differentiate. Okay, also the ability to touch with analog sensitivity. Not as sensitive as that hand I showed you. That's the first bit of a new robot that looks like the cartoon that I started with. Let me give you a small, and I hope we do have audio, because I don't know why we've lost audio. Let's see. Can we get audio back? Do you know what just happened? I was wondering why that last one didn't play. From everyone's silence, I'll take it whoever knows the AV system is not in the room right now. Is that?
Are you getting output from the machine itself?
Yeah.
On the local speaker you're getting.
So on the local speaker.
Yeah.
But we're not getting it on the host speakers anymore. It was working, but it died, it seems. Ah, yeah. I wonder what happened. Geary to the rescue. Well, if we have time, I'll go back and show you the description output. So here's a little clip. You'll see an example of the robot resolving some ambiguity and translating some simple spoken requests for actions into action. Okay, and what's happening along the way, words are being decoded, unpacked into sensory motor representations, translate to goals. Okay, and what we're going to do is then step through some of that in terms of the underlying framework and look at how it works. But first, just to get a sense of the behavior.
Ripley, hand me the red one.
So that's an easy one. Notice he doesn't say, hand me the red cup. This is based on properties, the red one. So red is enough to disambiguate.
Ripley, hand me the blue one. The left one.
Just to set the stage for something you're going to see in a minute, the decision to ask which one is driven by an ambiguity. There were two colors that were blue. There are other kinds of ambiguities in these little physical worlds where you don't need to ask questions. For example, if I say, give me the heavy one, maybe you can just figure out for yourself which heavy one, whereas which blue one, it doesn't appear to be any more information that the physical environment can provide. So in fact, when I said a theory of action that combines language and physical motion, there is an example. When I want to get more information out of my environment, should I ask questions or should I just reach out and do a physical experiment? And if you can do either, how do you trade them off in terms of a decision theoretic framing? Seems like apples and oranges, when to talk, when to move, but they're not, because we're solving it every moment of our waking day. So that's this is a picture of the underlying cognitive architecture that has all sorts of elements for doing perception and control and memory and setting up goals for the planning system for the robot that I'm not going to unpack, because that would sort of give you the engineering view of things. Oh yes, I forgot I put this slide in. I'll make one comment about a range of applications. If you come to the Media Lab, we'll be able to show you very fun demos. If a robot is a physical system embodied in some environment shared by humans, and it can perceive it, it can act on it, and you can talk to it, that's a pretty general model way of thinking about lots of devices, not just robots. For example, the lights in your house. So what started as a joke, hey, why don't we make a robotic chandelier, turned into this strange-looking creature, which has a camera that looks down, moving eyes that rove around. We have a cute little video here. This is a very early hand cam of Elvis, which is what this robot's name is. Elvis has little lighting elements. It learns as it moves its light tentacles around some given space, the effect it can have. And we have a simple, really from old view of homeostasis, where when a person turns a light off in the environment, the target state and the world state don't match, and a little closed loop control moves the light over to compensate. So that's sort of the framing. And then you can perturb it by talking.
Shine light over there.
So you tell Elvis to shine light over there. You've just changed the target state. So the translation problem is from words to target states in an illumination map. And in this case, Elvis swings into motion, recruits 2 lights in this case, and hits the goal state. Okay, but just thinking about language understanding in a homeostasis view, where you think of the meaning of a word as affecting change in a target state. Okay, and then having planning algorithms that are running anyways to try to maintain homeostasis, which get perturbed and get kicked into action. What's the status of the meaning of a word in this little guy Elvis's world? And I'll claim that there's something closer to sort of that holistic view, although for a very primitive system than other ways I can think of. So we have a bunch of systems. Okay, we're building more. If you went to our lab, you'd see now a car simulator. We've got a slice of a BMW 5 Series car we're thinking about conversation in cars, where you've got GPS, you've got time of day heading, you've got memory in the car. You know where you've been. How do you have a conversation with a robot, in this case a car, that's embodied, that can sense and act in an intelligent way, where that situated, grounded nature is at play? That would be another example you could come and take a look at. So what I'm going to do now is shift gears a little bit and talk a little bit about an emerging framework that I'll just characterize with 3 main points. First of all, it's truly driven by implementation. We've built a half a dozen systems now, and there's certain recurring elements. There's categorization processes, there's sensors, there are little generation processes, there's certain kinds of graphical structures that are emerging in the representations. And it was getting harder and harder within my own group for us to compare systems and talk about what exactly is the new insight in this particular piece of engineering that we've just done. And so I felt a growing need to explicate those underlying elements. And for us internally, it's serving as a framework for future designs. So what I'm going to talk about today is the basis for several conversations about systems we're planning to build. And it's not done. There's a lot of missing pieces, evolving, it's incomplete. This is a picture of the first page of a paper, which I've just written a draft of. And if anyone's interested in this experimental part of the talk, I'll be more than happy to send you a copy, because I'm looking for feedback that's trying to lay out this framing that I'm sure I'm not going to do justice to right now, because again, this is a slide I made this morning in my hotel room, so I'll tell you how fresh it is. So here, in a nutshell, is the way I'm thinking about grounding language. there's an object out there in the world. Imagine that's a monster fly on the screen right now. Okay, so it's a physical thing. This little translucent thing, imagine, is a configuration of photons, as we were talking about before, that is projected off of this physical object due to the causal nature of the world, and impinges on this sensor, where it's transduced into a representation I'm showing here visually, some levels of illumination on a retina. Okay. From the inner life, mental world of an agent that has, of course, no direct access to this entity, all it can do is monitor these incoming signals, and it gives rise to two very different kinds of signs. A natural sign, okay, which is a indication of the actual, the what. What is it? It's a fly. It's black. It's a certain size. It's a certain shape. Those are all I'm going to call natural signs that tells you what it is you're looking at. Okay, so examples include the touch signs and the visual signs of the cup that we looked at earlier. And there's a very different kind of sign, which I'll call an indexical, which is the where.
The what?
Indexical.
No. Which is the where?
The where, the location in space-time. So when and where did this sign occur? And so this is giving space and time very special status. It's saying the color of this object and the size of it and the weight of it, et cetera, are all of a very different type of class of property than when I'm looking at it and where in space it exists. Okay, so space and time are being given special status from the very beginning. And there's another kind of sign, which I'll call an intentional sign, which is, again, of a different category. So there is a fly here. Perhaps the most basic kind of speech act, in my opinion, there can be, is assertion of the existence of some entity in the world. Okay, it's a little set of words that are positing a claim about the world. It's a sign. Right here, there are photons hitting your retina. If you saw the fly, same case there. If you heard this in speech, it would just be air particles vibrating. So a sign is a physical pattern in the world. But the difference is there are natural laws that map directly from this to this. There are rules of convention by which these signs have meaning. And so the intentional sign is something that's generated by a volitional agent with the purpose of communicating. That sign is not. That sign just happens because physics happens. Okay. Fourth and last distinction I'll make is another kind of intentional sign, swat that fly. Okay? That's, of course, not a description of how the world is. That's a description of how the speaker would like the world to be. Okay? It's setting up a goal. It's a directive. So some of you might have looked at speech act theory, and if you go to Jarofsky and Martin, you'll find a whole taxonomy of speech acts. Some people have said there are 600 of them. Searle said there is a smaller set, but they are assembled in a tree and so forth. When I think about speech acts, I want to simplify even more. And so perhaps the most simple distinction is between a descriptive and a directive, where a descriptive is trying to tell you something about how things are. And that's interesting because that sign and that sign are doing something very similar. They're both describing. This is underspecified compared to this. This does tell you it's here and it's now. It doesn't tell you what color it is, what orientation. So there's a level of specificity problem. But the underlying format by which the agent should interpret this sign and these signs should be the same format, the language of entities.
Back to the distinction between the natural and lexical signs. Are you essentially looking for invariance, meaning the natural signs are the invariant parts of the object, meaning the fly is a fly no matter whether I look at it this way or that way or some other way, whereas which way I'm looking at it right now is an indexical sign?
Even prior to that distinction is simply when I have this form hit my retina, let me just put it in very straightforward terms, the XY coordinates of its centroid, okay, I'm going to treat as special, different from the radius of that blob, the color of it, the orientation of it. I'm going to call the X and Y, and when I took that reading in time, to be special. The reason it's special is in order to encode the situated nature of an object in terms of how it relates to others in the scene. Time and space keep turning out to be special in all of our code, right? We like to treat space and time differently. That's as much as I can say about the justification.
Instead of a fly, let's say I put
Mhm.
a chair over there, and
Mm-hmm.
let's say I turn the chair around in 5 different orientations.
Mm-hmm.
Then which parts of it are the natural sign? And for example, is the orientation of the chair an indexical sign or a natural sign? It's in the same place but turned around.
Yeah, I don't know, because we throw out orientation information because right now we don't know what to do with it. So when we're dealing with a cup in different orientations, all we have is a set of distinctive views and transitions. The only thing we bind language to is a higher level abstraction which says one of those views holds. So very good question. I mean, if I had to answer right now, I would say, I don't know. I'm not going to try to give you an answer right now. But hopefully the idea of where it's located in space-time, setting aside orientation, is sort of a kind of a more coarse level description.
So a different way of looking at that distinction is that there's one view of semantics that says that the purpose of semantics is to assign attributes to indexes. So that everything is an index, either a physical index here and now or an abstract index of a thing that could exist.
Mm-hmm.
And the purpose is to take objects in the sentence and to figure out which of those indices is bound to each of the objects in the sentence.
Mm-hmm. Yeah, I don't know. So and I suppose you're thinking of that because I chose the word indexical?
Maybe.
Or maybe, yeah. Maybe those are related. I'm not sure. Let me try to push forward a bit. So maybe the thing I didn't mention, the two main ideas that I'm trying to bring together. One is very classic ideas of semiotics, which those of you who are familiar with semiotics has seen by now, which is don't treat symbols, language, words, speech acts, don't treat them as special, as different from the world of physics and flow of photons and electrons, which often tends to happen. There's sort of this sort of boundary drawn around the world of symbols. Instead, see them as just part of the family of signs, right, and try to blur that distinction and connect them. Right? And the other is an idea that's had much more of a foothold in computational work, which is schemas. Right? Going back to Kant and Bartlett, but in more modern times, Schenck and Minsky and Rumelhart in the 70s, people like Drescher in the 90s, and really in a lot of systems we all engineer, where you've got a frame that you're going to fill the slots of, you've got schemas, or you've got some sort of a structuring, a data structure which constrains the possible interpretations of stuff coming in. So it's a very general idea. We all, in some form or another, probably have used it at some point. So this is in that family. I think the semiotic perspective, sort of bringing those together, is really what gives us a unique sort of a spin. So there's the equivalent of our fly now, external object. What I'm doing here is introducing a simple set of elements that will make up these graphical structures. We have nodes, which are beliefs, okay, and we have projections, which are transformations from one belief to another. When you have a structured set of these beliefs with their projections, you get a schema. Okay, a schema is used to stand for things in the world. It's used to interpret incoming signs. It's used to make predictions about what's going to go back out. And it becomes the substrate that you connect words to. Okay, and that's sort of in a nutshell why build up these schemas. And I think rather than going into a lot of detail, what I'm going to do is go very quickly, give you almost the texture of it. I show you the paper unpacks these things in detail, and then maybe we just take questions. So an object projects a sign which is transduced into an observation. An A sign is a belief about an analog sign. So it's just a distribution over the domain of this observation. So that might be, for example, possible foreground-background contours. That's one of the sort of A signs we have in our system. So this is a projection. Okay, that's one possible edge element.
Excuse me, how do you generate the A sign?
In this case, in this projection would be the machinery to do foreground, background.
Is this the generalization? In other words, you see a projection and you generalize it because you actually know things about the world, and therefore it's probably a cup. You only see a projection of the cup.
That's right. No. This is all this is a graphical element of a descriptive language for the kind of structures we've been building, where this particular one stands for a space of possible projected observations from the world.
So it doesn't. So it does not use our knowledge or belief that things that project this way probably look
No,
that way.
not yet. That's what's coming later in the chain. This is an analog transformation. There are lots of those in our code. Basically, these are feature selection and continuous transforms on features. So for example, here is a shape histogram, which is one of the features we've developed for characterizing two-dimensional shapes. That's just showing that you can go from a particular pixel map to this more abstract and useful encoding. That's scale and size invariant. And then to answer your question, in a sense, the magic happens, right, which is knowledge that there is a particular subset of this space, which is interesting, which we want to call a cup. We can't just label it cup and be done. That's meaningless to the machine. But in terms of a categorizer that makes a discrete decision, one of the discrete outcomes of that categorizer is that it's of this category that we're building towards, which is a cup. Okay, and in general,
This is the generalization.
Sure, yeah. Or this is the point where theory happens from a mental perspective. This is where the latent variable is instantiated to explain away the observation.
But I don't still understand what the transformer does.
The transformer is just doing, for example, another transformer could extract a color histogram instead of a shape histogram. It's just, it's abstracting, destroying certain information and choosing other information, but in a continuous space without making a discrete decision. All right. So this is just a straightforward, I'm using weird elements to draw something standard out of a pattern recognition text so far. Okay. The reason I'm doing this weird stuff and trying to think of it in terms of signs, both analog and discrete beliefs and signs, is then we can bring in the perspective of semiotics and push it into the symbolic domain, okay, working our way up from sensors and actions. So sensing and transforming were two types of projections. A third crucial one is action. So you can think of it this way. You have your gripper. A action primitive is any of the motors in the robot. When you close the gripper, that's a transition through one of these edges. And actions will binary, discrete outcome, either succeed or fail. Did the gripper close or not? Okay. What's interesting to me about this is a discrete outcome, just as you get one out of sensing. So as a sensor can lead to a discrete outcome through categorization, so can an action primitive. Okay, so in fact, the way I will interpret this is it's a sign, okay, about the world as well. I've acted and the world is pushed back in some way. Either I've succeeded or I've failed. If my beliefs about the world are correct and I'm using them to guide my action, then in general I should succeed. And when I fail, that's surprising. And I should go and investigate and revise beliefs. Okay?
Well, it may be that the machine is not adequate to grab anything, so it's not.
But if I believed I was adequate, then...
Well, you tried it. Okay.
Yep. Yeah. So, but again, if your model of your own affordances, what the affordances are, which is a function of the environment and what I can do with it, I'll have to revise that piece of my belief network. Yeah. One more piece, and then I can put them together. So one of the first things we did with Ripley was we tried to teach Ripley the meaning of soft and hard, right? So if you think of soft and hard, that's a function of acting upon an object and seeing how the object acts back. So I make contact and then I keep pressing, and can I deform the object or not? Okay, and that's not just a succeed or fail, that's actually a sense what's happening along some dimensions of my sensory apparatus while I act. Okay, so there's a simultaneous sensing while acting, which I'm trying to explain through this little structure. So here we take the action of gripping and we sense what's happening and we get a new A sign. Okay, we get an analog observation, which is again about the world. Okay, so that's sort of capturing all of the active sensing elements. So now we can build higher order actions. So in order to lift an object from one location to another, we can pass parameters. We do this with Ripley. We've done this with Newt, one of the other robots, where you tell the system to search for an object by hand or visually. So L is an indexical sign. I'm wondering what level of detail I should do this at. Let me go up a level and just say, to read this from a robot's perspective is to say I should be able to touch an object at L and then close my hand and succeed at doing so. I should get some touch sign on my fingers, which when I categorize should seem stable, in which case I can move my hand successfully. And that whole chain put together is essentially a procedural view of a schema for how to act upon an object and do something with it. Okay?
So that means that the robot monitors this.
Yes.
And will not proceed
Absolutely.
without it being confirmed.
Mhm.
The successive successes
Yep.
being
Yep.
confirmed.
And if any of them fail, that means something about what led it to instantiate that structure is mistaken. Yeah. So this is the, maybe we'll put several of these pieces together. What's an object from the robot's point of view, given this reading? Well, here is this root node, sort of theoretical node, the latent variable that's instantiated to belief in a cup. And here is the indexical, okay, that goes with it, that says something about where in space and time that existence is being posited. And all of these different loops are how to look at it and what to expect if you try to manipulate it. Okay, so here is that lift schema I just showed a moment ago. And this is making a prediction that if I go and I try to run this particular procedure, it will succeed. And by the way, the indexical will be refreshed in the process. Okay? So here's a little set of instructions for how to move an object around. Here's a little set of instructions for how to visually detect a region and characterize its shape and its color, and certain expectations on what shape you expect to find if you were to look at it, given that it's a cup.
But you have to pre-specify the set of actions, closed groups, and stuff. So for example, if you are going to drink coffee, you'd have a different set.
Yep.
And you have to specify them. That can't be learned, right?
That's correct. In fact, the way we specify them is we build hardware. And every motor we drop into a robot gives us a natural action primitive, which is move to some target location. So it's PD control loops throughout. Move to a certain location with a given trajectory in space-time subject to certain failure modes so that you don't keep moving if you can't. And those are the primitives.
So supposing I was to extrapolate and say, I'm going to build like a human robot who has a large repertoire of actions.
Yep.
So you'd have to specify, do you know how large this could get?
Yeah, well, we're building right now a robot that has about 40 degrees of freedom, 2 hands, 2 arms, upper torso for active perception. So the simple answer is, at the most primitive level, 40. Now, in a human, you have sets of muscles that act together. So you have to do some sort of approximation that where the motor primitives come from in that sense. But it really grounds out in the actual physical system.
Yeah, but is this
And it's
one set for each set of muscles, or is it one set for each kind of action? Like,
each
you know,
set.
I may use the same set of muscles to.
No, the answer is for each muscle, not for each action. Otherwise, the primitives become open set. So for example, take Shank's scripts, right? What are the primitives? Well, there are these 11 very nice action primitives, and then he applies it to the restaurant domain, and he has primitives like price list and menu and so forth, right? And that's, in my view, problematic because it leaves objects as primitives. Objects are not primitives. This picture is saying that what it means to believe there's a cup is to have a set of beliefs about the things you can do in that situation. So actions, properties, are subsumed by an object model. It's not that an object is a primitive. An object is made of the same primitives that actions are made of, and the same primitives that properties are made of. Okay, and this idea of what an affordance is, given some novel situation, what can I do in that situation, is a function of all of these underlying properties, which are the language by which the control system for that same system and the perceptual system for that agent would be constructed. So it's trying to distill all of those different views down into the same set of primitives. Okay. This is a little, what happens when you show Ripley a photograph of a cup. Okay. Well, this part looks the same. This part doesn't. Hand contact, we expect failure, and therefore this entire loop gets blown out. What's the difference between a photograph and a cup, given this view? It's that. What happens if you show Ripley a cup, and Ripley, I haven't talked about it yet, but the interpretive process decides that's a physical cup? It can verify by reaching out and then touching. And if it fails, it can revise and say, whoops, wrong belief structure, right? Let me reinterpret. What's that?
It can also try and reach out for the photograph. So does it know something about
It'll fail. Ripley is clumsy. If Ripley is trying to grasp, it can only grasp 3D objects above the table. It can't actually trace outlines of the table.
Well, and presumably, if it were able to grasp it, it would discover it had a
completely different.
Unexpected.
Absolutely.
Only if it looks at it from a different angle.
Yep.
What I'm curious about, there must be a lot of attention that you've devoted to control.
Mm-hmm.
So when do you decide
Yep.
that you're going to try to verify? When do you consider the latent variable to be sufficiently uncertain and your knowledge of it to be sufficiently important that you'll go and initiate some action to discover what's really in the world?
The truth is that part of our system, we have spent a lot of time on control. I don't have slides on it. We have it looks a lot like Asimov's 3 laws of robotics we discovered after the fact, right? Which is don't crash into things, do as you're told, and keep your the heat in your motors low, because we just burned out another motor, right? So, and it's sort of those 3 top-level goals. Struggling for control of Ripley's body. When you tell Ripley to do something, it pops up a node, it pops up in a higher priority than the other goals, and that takes control. When there's ambiguities, like is that which blue one, because I can't tell them apart, the decision to make that speech act to say which one, right now, hard-coded the pathway from that ambiguity. So there's certain pieces of the puzzle to get it off the ground we've hard-coded. I just had I was talking to Joe Halpern, who thinks about these things in very elegant ways. And he looked at it and he said, how are you going to do efficient inference on this structure? And, and sort of questions that I haven't thought about, because we're like, well, yeah, good question, right? So, which I see as, that's a paraphrase of what you just asked, I think, which is, given some sense data, I have an ambiguity, a two-way ambiguity between, is this a photograph or real, or is this a cylinder or a ball, because I see a round form. Well, I could take an action and distinguish between the two, but should I? Because if the person said, give me that thing, it doesn't matter if it's a cylinder or a ball, they're both things. And so there's sort of a decision to be made there. And I don't have sort of as well-formed
It might matter if it affects your strategy for picking it up.
Mm-hmm.
So you might
Yep.
look at it a little more carefully before you try to get it.
Yep, that's right. So let's see.
Also, it's more than that, right? Because there are multiple actions that you could take to try and verify whether it is indeed the object but to verify the hypotheses that you believe you're holding right now.
Mm-hmm.
And each of them is going to fail to different degrees, meaning,
Yep.
for example, an easy action might be not to reach out and grab it, but just to change your viewpoint a little bit.
Yep.
And see if what you get is consistent. And then that might not cost a lot, but it may also not resolve some of the ambiguity.
Right.
And there's a whole strategy. You're saying that you're avoiding that by hard coding it and saying.
Well, what I said is, thus far, because we haven't put enough energy there, we've hard-coded some of that. We have done some work on, the reason I use that example of is that a circle or a can, kind of starting from that insight, we have a decision theoretic framework for deciding when to ask disambiguating questions versus when to probe the world to get more information. So that's a little piece of that puzzle that we have some nice results on, but it's part of a much huger puzzle, so I didn't want to just present that one piece today. I'm going to skip forward a bit here because I haven't said anything about language in this schema yet. Here is a word. Okay, what this word is, because it's shown in this rectangular block, is a discrete category. It's part of the lexicon. It's connected through a pair of paths to be able to map surface form to and from that discrete form. A lexical item in this view is a piece of theory. Right? Discrete words only exist in heads, okay, minds of communicating agents that are then mapped into surface forms through sensory and action projections, just like any other sign. This is a new symbol, this little join function. What this reminds us is, as opposed to this entire structure, which is constructed from natural and indexical signs, okay, this is an intentional sign, which means you have to be careful when you apply this as a projection that looks like a description. And that was probably a jumble, even it sounded jumbled to me. If you hear a speech act which you decide is a descriptive speech act, it's somebody who you trust, who's making an assertion about the way the world is, then you modulate this into a standard projection, okay, and it will instantiate one of these structures. So just like I see a cup, I hear a cup, same structure gets instantiated in the robot, okay?
I say cup.
Yep.
That means that goes down there, and then I try to verify.
Mm-hmm. You could, yep. Or, but not just, if you say cup, just cup, right?
If I say this is a cup.
Very different, right, yeah. So if I say this is a cup versus give me a cup,
Yeah.
that basic distinction between directive and descriptive needs to be made. If you decide it's a descriptive, then you have to decode the situated aspects. There is indexical signs hiding in that. For example, this is a cup right here, right now. If you were to be so explicit, we usually aren't, so that makes part of the problem
But
hard.
would I check it in fact? Would I check it? Whether it,
It depends. It depends on if you have a goal that involves that object. You may simply construct the model, and then maybe the person will.
there is no visual checking, right? In this schema.
This is
Only the touch.
no detect visual region should succeed. Sense region, measure shape, measure color.
There is no success or failure up there. So
Success. So detect visual region, success or failure, right there. So this is a visual routine which says sample my distribution over the indexical space and detect a visual closed form region. And if the routine fails, then there's no object. There's no visible object. Yeah. I'm going to wrap up here. Yeah. Here is that heavy schema at work.
Ripley, hand me the heavy one.
The mental model by vision, we're seeing a little animation of it. There are 3 object schemas that have been instantiated. Their weight is unknown, so that part of the belief network has high entropy. So we have a action that's being taken in order to fill in missing values, just like the robot could ask a question. This is now a Ripley-centric weight measurement for one of the objects. It will run through that procedure for all 3 in order to fill in the property that this particular goal relies on in order to pick the right object. It's funny, I've got 5 minutes left, so I'm just going to play one more video rather than talking. This snowman, by the way, see this guy here? That's a stand-in for where Ripley thinks the human is, which is connected to a face tracker. And you'll see that in a minute as well in that last video. So now missing data is filled in, and the heavy object is handed to Caillou. There are ways to build these structures up. So if you want to represent something is touching the cup, of capturing ambiguities and having spatial relations, not going to unpack them, and simple temporal sequences of situation. There was a ball was in the cup, now it is not. If you'll take the, just trust me on this. This is one way to encode temporal relations using exactly the same set of elements. So we're not adding any more elements at this point. Put the cup in the plate is just showing a desired goal state, again using the same elements, but showing a difference between some part of a situation now versus wanted. That's our way of describing plan targets. And here's another little bit of video that shows the face tracker at work. What this is about is thinking about frames of reference for indexicals. So if I say the object on my left versus your left, you need to know something about points of view.
Why is he going around?
Why is he tracking? He's the face tracker is in.
No, I'm talking about why is the man moving around?
To show you what it does.
Then it will track.
Yep. So he says, touch the one on my left. In Ripley's mental model, we get a shift of views. So we're now actually, this is the world from the speaker's point of view rather than the listener's point of view.
Ripley, touch the blue one.
You mean this one? Or this one?
Touch the one on your left.
And so this is just to get the fact that
Ripley, pick up the green one.
your left versus my left, that we get that modulation. So it's sort of a fun piece. So just to conclude that piece then, really, if nothing else, kind of the highest level, if you go away with this idea of combining semiotics with schema theory, a set of elements, signs, beliefs about signs, a set of actually 6 projections, if you counted them, that lead to these schemas. That my claim, which I haven't fully unpacked in the time I had right now, is that we start to see a continuous path from sensing and acting to words and to speech acts. And lots of stuff here I'm not going to talk about. Okay, let's see. Neverwinter Nights. This is a virtual game with lots of agents who can talk to each other to do goals. About a third of my group now, so 4 people, are working on this one platform, looking seriously at situated speech. When people are excited, trying to coordinate actions, saying things like, don't do that, try it again, I'll be there in a second, a lot of that kind of speech, okay, which we're recording in raw form. And we're trying to analyze in terms of formulating it in game theoretic terms. And let me just unroll this. Detecting what game some set of agents are playing, what roles they're taking, what goal each speech action and motor action is trying to pursue by situating it all in a common framework. So that, in 30 seconds, is a view of how to think about action analysis. We're building various new tools, so this is a way to annotate, not just transcribe speech, but literally draw links from parts of speech acts to reference. This is a little playback visualizer of games, so we can get this situation binding of parts of speech to the stuff it's talking about. Often people talk not about physical things, but about actions and goals. So we're doing some work, Michael Fleischman and others, on using stochastic context-free grammars to do plan recognition. So here, as people are moving about the world, multiple hypotheses of why they're moving are being generated. And the reason we're doing this is often language is binding to some hidden structure in these plan fragments, the decodings of the plan fragments. And so this is going into then the annotation system. I'm going to skip all this here, and if you let me just give you a plug for in case I talk to you afterwards. There's something really broken about what happens in certain situations when you measure information in terms of bits. This is husband says to wife, "I love you" every day. There's no surprise in hearing it, and so there's no bits. I really think there's an interesting alternate way to quantify information structures that gives you something more along the lines of the kind of impact or significance factor that those words actually have. And it falls straight out of this formulation. And I'd love to chat about that. So in conclusion, meaning machines, what have we done? I've tried to pitch to you a picture of meaning holism, which captures far more of what it is to talk about meaning of words. I've given you a definition of grounding, which has to do with a causal predictive loop between beliefs and the world. I have shown you several embodied architectures that actually try to build out parts of that space. I've presented fragments of a theory based on schemas and semiotics that tries to formalize some of that. And the part I really whizzed through today, first steps towards thinking of fine-grained game theory as somewhere to bring those two threads together. And I'll stop with that. Thank you. My watch says we have about
2 minutes.
2 minutes.
So mostly in the talk you talked about physical objects, physical representation of physical objects.
Mm-hmm.
Thought about how to represent abstract objects.
Mm-hmm.
And it seems like one way to go would be looking at metaphor
Mm-hmm.
from physical representations.
Mm-hmm.
What do you thought about
I think that's definitely an interesting idea. We've looked carefully at a lot of there's a standard view of kind of computational models of metaphor, which are basically structure mapping, which I think are problematic. There's some nice work by people like Hollyoak and Thagard on sort of combining similarity metrics of nodes with structure, which could definitely apply to some of the things we're doing. I take seriously Lakoff and Johnson's observations about metaphor structuring not just language, but people like Boroditsky have shown that we really do think in metaphor. One domain shapes another. Having said all that, one important, I think, message in the way at least I view things is even the most physical, tangible, concrete things that you feel are right there, you're building theories of. And it's a leap of faith. It's an inference you're drawing, and you're constructing this latent variable. So I don't know, I've made it myself, the distinction between concrete and abstract. Clearly, there's layers of complexity. To get to social sorts of constructions that you can talk about, there's many layers of, people call it theory of mind. I want to unpack what theory of mind is. So who knows what the elements are? But I see a continuous path. Sometimes people think of metaphors as sort of just bootstrapping, sort of jumping from the physical to some very far away domain. It may be happening much closer to home. So Boroditsky is really interesting on the cognitive science side, saying that we think of time as if it's space. Two things that you would think are both very concrete, that one is structure and the other. So it might be more just, so what's the status of metaphor? If you talk to Hofstadter, he'll say every similarity metric is a metaphor, right? Is an analogical mapping, right down to that Euclidean distance measure you're using way down there. So there's, again, a way to see all of these as continuous. But the stuff, you know Mike Fleischman, and he's working on grounding words, doing verb acquisition in that Neverwinter Nights, so is Peter Gorniak. That's less about the physical objects, more about what people are trying to do. And they're playing games, so they have some set of joint goals, and they're acting in coordinated ways, and often talking about each other's goals. That's pretty abstract, right? Don't try that again. What's that? Well, it's some action I took, but maybe not a physical one, but a whole class of actions. That's starting to get abstract, but it's got roots on the physical side. It's tempting to go off and, build systems that talk about democracy, and I see that as problematic because maybe you want to and so go off and do it, but without some sort of a path of continuity, which I believe exists in the most abstract concepts, including things like democracy. We probably ground out something like democracy in some specific cases, which have, so but yeah, we are down in the basement. But if you want to analyze speech of people interacting, having those elements often are the crucial ones to making sense of otherwise simple semantics. So we also have people playing games in Cambridge, in Kendall Square. We built some wearables with GPS and audio recording where people can go play the real games out. And So there's some interesting kind of practical types of domains. But yeah, so that, I guess, is my answer to getting at abstraction.
So just to follow up, it seems like you kind of alluded to this earlier. You and Rodney Brooks have kind of a difference of opinion about even the existence of structures and symbols in thinking. So you kind of have a lot of structures and symbols in the way that you do processing. It seems like that is kind of, I've always felt that that was necessary for building up any kind of larger abstractions. But maybe, I don't know, what would Rodney Brooks say now?
So Rod would, so here's my take on what Rod did, which is he saw a field which was here, and I think if he really dug down, although for a while this maybe wasn't the case, but he believed the field should be here. But he's only this big. So he went here and said, this is the way things should be. And he kind of, he got a little bit of motion for the whole field. So I think he accomplished something really important. If you talk to him now, I think, especially since he directs this thing called CSAIL that has lots of symbolic kind of people under his directorship, he holds a more moderate view. And he of course knows about this work and is quite sympathetic to the view. I still like using him as an example. Brooks, circa 1990, right? Intelligence without representation. That's intelligence with a lowercase I, right? You're not going to get far without building more structure. If you look at what's happening in his group, or what was happening a couple of years ago when he had a full-scale research group, they were building lots of structures into the system. They have to be there. And again, the way to I think, present an irrefutable case for that is we can describe what we see and do. And descriptions are made of symbols, unless you want to deny words the status of symbols. So there's no argument against it. It's just a question of, do you want to worry about language or not? So, but from the robotics domain, this comes long before, back in the days of Shaky, every roboticist knew if you want to build a robot that can navigate to the light source in the room, don't tell it where the obstacles are. Don't tell it where the light source is. Tell it what a light looks like and tell it how to recognize an obstacle when it hits one. Give it a map, but let it question the map. Let it verify and let it detect when it bumps into something and back off and try again and maybe revise the map in the process. So that closed loop feedback, which every roboticist knows you must have, no matter how good your descriptions of the world are. The descriptions are always your conception of the world, which will be different from the robots. And the same argument goes for language. If we're going to build up semantic theories that are built on my conception of, well, damn it, there are objects, they're chairs, so that's a primitive. And they have color, so that's another primitive, red. Chair has color red. Whatever, however you want to express it. Stick probabilities on it, doesn't help, right? It's my conception of the world. If it's wrong, because I don't fully introspect, or if it's divergent from what this machine is capable of doing, we've got a problem. And we've definitely got a problem in terms of, Oh, thank you.